Hello, good morning. My name is Diego Reis. I will present due to the impossibility of Carlos attending to the event. Um, our project is the subject is surface properties of commercial 3D printing resins for optical applications. We work at EDMEC, that is the Mechanical Institute of University of Lisbon, in Instituto Superior Técnico, and the project is under AM Optical. This is an outline of our project. I will start giving an introduction about additive manufacturing. As you may know, AM presented a significant growth in the last few years with a compound annual growth rate of about 20% between 2016 and 2021, and it's expected to increase even more in the next few years, reaching a market value of over $35 billion by 2027. Recent advances in this technology allowed it to extend to different domains such as biomedical, automotive, aerospatial, and others. And this technology offers a new perspective on products that lack on widespread accessibility due to high manufacturing costs, minimum batch sizes, or long lead times. One example of this is the optical industry, in which produces optical components by molding or by cutting a slab of glass, followed by precision shaping through grinding and polishing, in which you can see in the image an example. But the traditional methods are quite time-consuming, inflexible, and cost-inefficient. Additive manufacturing can address all these issues by simplifying the whole process, reducing costs, increasing speed, and leading to a more flexible and feasible process. One promising technique of additive manufacturing to the fabricating of optical components is stereolithography, in which it uses a UV light source to cure a resin by photopolymerization. And it's promising due to its properties, for example, high resolution and high precision. And also it presents a good availability of clear materials, which is not found in other additive manufacturing techniques, for example, fused filament fabrication. Here in this image, you can see an example of masked stereolithography, which is the technique that we use at our lab. It uses LCD mask to filter the UV light source in order to cure the resin selectively. However, to obtain optical components by 3D printing is not a straightforward process, because right after printing, it has an opaque appearance, and this comes from the layer-by-layer methodology. So the effect is called the staircase effect, and to remove it, there is different methods that can be applied. For example, grinding, polishing, and coatings with the same resin. For example, deep coating, spin coating, and spray coating. The one that we use is deep coating. As for the experimental procedure, we first started with the resin selection. We knew that we needed a transparent resin that was washable in alcohol. We also wanted a resin that presented a good availability on the market and resistance to yellowing, which is one of the main problems of polymers. Mainly the transparent ones, and we tested different resins, but some of them presented poor quality of the cure of the coating. One example of this is shown at the first image, where you can see that some patterns were formed. This is due to different gradients of the UV light absorption. Some of them also presented yellowing and low availability of some resins. Some manufacturers discontinued. So this is one requirement. So this is one of the requirements that we selected to have a good availability on the market, so you can continue to study it. So the best one that we could find was any cubic high clear resin with the following properties. For obtaining this the STL files, we intended to print 3 different lenses from Edmond Optics, 1 plano-convex and 2 double-convex with different thickness. We selected those lenses because we want to make a further comparison with the original ones, and so we obtained the CAD file in the manufacturer's website, and then added a frame support to make the deep coating possible. The slicing software was Prusa. We printed in an orientation of 60 and 70 degrees with a uniform support distribution in a continuous way in order to prevent some defects that could appear in the printing step. Also with a support head diameter of 0.2 millimeters. Here, in the 3D printing methodology, it's possible to see in this fluxogram. First, the STL file, then the slicing software, the printing. This is the Prusa SL1 that was used, and the printed part with the support structure and the frame. The layer height was the minimum of this printer. We used 25 micrometers with a layer exposure time of 20 seconds for this resin, which was a bit higher than the other ones that we tested. Here is a zoom of the printing, and then the process treatment, which is the critical part of the process, because it will give the final appearance of the lenses. So first is the washing in alcohol of the printing, then UV pre-cure to cure the remaining resin, and then the support structure is removed and the frame is attached to the deep coating equipment, and the coating is done with withdrawal velocity of 25 millimeters per minute. Then the coating cure. Also, beyond this step of coating cures, there's a second step of the cure of the coating with washing alcohol in between to remove some sticky surface that could continue after curing. The majority of these steps are done with Prusa SCW1 cure station, which shows that is a simple process but with many variables. Here is an example of the printed lenses with the coating. And for the resultant discussion, the surface roughness was measured by a 3D optical profilometer. The best line roughness that we could get in a distance of 400 micrometers was 170 nanometers, what is a bit higher than the minimum requirements for optical applications with a lambda of 635 nanometers, and the optical transmission was obtained through the following setup: the optical source with a laser beam, then the 3D printed lenses, the sensor, and the optical power meter. The radiation that is transmitted through the 3D printed lenses is measured, but there is also some optical loss that there's two types of optical loss: the absorption loss and the scattering loss. The absorption is related with the chemical composition of the resin, and the scattering is related with its surface defects. The measurements was possible to obtain optical loss of about 20% for a 3.5 millimeter thick, and with data obtained in the manufacturer's website, we could calculate absorption loss of about 1.55 dB per centimeter, and with the difference, we could assume a scattering loss of about 120 dB per centimeter. Is also reasonable to say that this percentage of optical loss is acceptable for most of optical applications. To conclude, stereolithography with the deep coating technique allowed to obtain transparent lenses. It's not a straightforward methodology due to many variables involved. The surface roughness was a bit higher than the minimum requirements for imaging optical applications, but the optical losses were acceptable for most applications. So the results were promising, considered the different geometries printed and also the cost efficiency of the process. So it shows that 3D printing of optical components is also an alternative in the future with further optimizations. And also some further work, future work is necessary. For example, a deeper dive on the slicer settings, further optimize the step of printing, and also some optimizations of the post-treatment are necessary. We want to do some mechanical characterization of the coating, for example, micro hardness and wear resistance, and also to do some coating thickness measurements in order to decide the best value for the withdrawal velocity, to decide the coating parameters for the best coating thickness. And we also want to test different types of post-treatments, the ones that I mentioned before. And this is my acknowledgements. We would like to thank FCT and the project AM Optical, and thank you all for your attention.
Thank you very much. The talk is open for discussion. Charlotte?
Thank you for your nice presentation. I have a question. Have you considered SLA printing the mold and then do resin casting? Because of course we need AM because not all lenses are as simple as we use in daily life. But what if you print a mold and then just cast it? Then you can reuse it, and maybe that reduces the cost even more than this. What do you think?
I think that it wouldn't be straightforward. I think it will have the same problem, because the mold will have the staircase effect also. So you can print the mold, but the mold will have the staircase effect. So after the resin casting, after you cure it, you have also the staircase effect. So I don't know if it's possible to have a great benefit from it.
But you can do the dipping on mold too. The same technique that you use here.
yeah, this is a possibility, but yeah, this is a possibility that I
It's just a suggestion, though.
yeah, but makes sense.
Yeah, thank you.